Okay, in this problem we're asked to determine ZL for maximum average power transfer and the value of the maximum average power transferred. We're going to rely on two problem solving strategies. One is the maximum average power transfer, and the second one is on applying Thevenin's theorem. And if we look at our strategy for maximum average power transfer, it says remove the load ZL and find the Thevenin equivalent. So here's our load ZL. We're going to remove it. So I'll show terminals A and B, and we're going to find a Thevenin equivalent at points A and B. And then once we have the Thevenin equivalent, we'll reconnect ZL and apply the maximum power transfer theorem. So if we look now and say, okay, from Thevenin's theorem it says remove the load and find the open circuit voltage. Okay. So here's our circuit with ZL removed, and now our task is to find the open circuit. Now let's make some observations. First of all, if I apply KCL here, the current is 3 at an angle of 10 degrees there. And if we think about and say, well, which technique should we use? We could do mesh analysis with two meshes. We could do nodal analysis. For instance, if we did nodal analysis, if we pick this as a reference node, there's a node voltage is known. There's a node voltage is known. Then our only unknown node voltage is a voltage V1. And if we apply Kirchhoff's current law at that node, okay, then we can find V1, and from that we can backtrack and get VOC. So let's apply Kirchhoff's current law and write a nodal equation. So we'll have V1 minus 12 over 3 plus J2 plus V1 minus 6 at an angle of 0 over J3, and that's equal to 3 at an angle of 10 degrees, because this current's coming, that source is coming right into that node. So if we solve for V1 is 12.28 at an angle of 34.5 degrees. Now, how can we get VOC? Well, we can apply KVL around that loop, and if we do that, we'll have VOC is 4 ohms times the current, and then plus V1. Remember, V1 is a voltage from the reference all the way up to that node. So we have 12 at an angle of 10 degrees plus 12.25 at an angle of 34.5. So then VOC is 23.73 at an angle of 22.39 degrees. So now that gets us the open circuit voltage. Next, we need to calculate the Thevenin impedance, and we can take our circuit there and turn all the sources to 0. Okay, so if we turn this to 0, remember it becomes an open. If we return this to 0, it becomes a short. If we turn this to 0, it becomes a short. Our resulting circuit for calculating Z Thevenin is here. And really we have this impedance in series with this parallel combination. So Z Thevenin is calculated as follows. Okay. And Z Thevenin then is 4.79 plus J 1.68 ohms. Okay, so now that completes our Thevenin equivalent circuit. Now we can draw the Thevenin equivalent circuit. Okay, we have 4.79 plus J 1.68 ohms. Here's our terminals A and B. Here's V open circuit And now we're going to hook up ZL. And if you look back at our problem solving strategy, it says now ZL should be equal to Z Thevenin conjugate. So it should be 4.79 minus J 1.68. And now let's calculate a current IL. Alright, IL is 23.73 over 22.39. We have 4.79 plus J 1.68. 4.79 minus J 1.68, which is 2.44 at an angle of 22.39 degrees. So now, this load is composed of a resistor and a capacitor, and that resistance is 4.79. So the load power is the power dissipated in that resistor. So P sub L is 1/2 times 2.44 squared times 4.79, which is 14.26 watts.